Welcome to the Problemas channel, season 3, episode 1, the episode which I titled The Index of Tools, because in this episode we will survey all the problem solving approaches that we have studied in a dedicated manner over the last two seasons, season 1 and season 2. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemas Channel How To. Watch that episode in its entirety. We recommend that you follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find any episode which is of interest to you, use the comment section, and I'll do my best to find the time to answer all of your questions. If you watch the material that we present on this channel on the regular basis, then you already know that a problem-solving approach is a heuristic template that does not really guarantee the production of a solution, and as such, the problem-solving approaches in general as heuristic templates sit on one side of the guarantee of the production of the solution spectrum, on the other side being an algorithm, which is a precise finite description of a finite number of steps, taking which the production of the solution is guaranteed. However, in general, in hard sciences, when we take on a problem, we have no way of knowing whether this problem has a solution to begin with and how many different solutions it may have. And the heuristic templates, otherwise known as problem-solving approaches, may help us unlock a solution or maybe perhaps multiple solutions to this or that technical problem. Now, if you came to this episode because you joined our channel later on, you can always compile the table that I show over here by yourself by using the links in the comments to this episode. And these links will point you exactly to the so-called season guides that you need, because this is the place where I laid out all the material that you see over here in the third column. Simply click on the link, go to Season 1 Guide and Season 2 Guide. These are the free PDF files in my personal GitHub repository. Scan through the files, look for the descriptions, and you will see that all this material is stretched out over the two seasons. And this is the summary of the table that I constructed for you, perhaps to save time. So here across 4 columns, I show the number of the problem-solving approach, and these numbers honor the chronological order in which we studied. We studied these problem-solving approaches in this specific order. Again, if you want to watch this material on your own, out of chronological order, that is perhaps fine, with the caveat that I will mention in the next segment when I will cover the remaining 6, because altogether we have covered 11 problem-solving approaches. In this segment, we'll cover the first 5, and in the next segment, we will cover the last 6. So there are a couple of nuanced and somewhat technically heavy problem-solving approaches that is perhaps better to leave for the remainder of your mathematical journey. So here in the leftmost column, in the first column, I show the number of the problem-solving approach. In the second column is the name. In the third column are the episodes in which I explain the mechanics of each and every problem-solving approach. And then we apply that specific problem-solving approach to the process of uncovering a solution to a given problem. And again, I use and try to use as simple material as possible, nothing complicated. I try to keep things at the level of middle school in order to explain how each and every problem-solving approach works. Now, once you understand the mechanics of how this or that problem-solving approach works, then you can apply it to any problem. The sky is the limit. There is no upper bound for the application of any of these approaches to any of the material. Now, in the upper right corner here, I show the number of episodes just as a quick summary. You guys can count on your own, but here with the quick glance, you can see how many episodes are dedicated to each problem-solving approach. And this is a symbol that you guys should recognize. This is a playlist. All the episodes that pertain to one specific problem-solving approach, I glom them together, put them in the corresponding playlist. You can see them in the last column over here. Usually the name of the playlist trails, mimics, or exactly shadows the name of the problem-solving approach. As such, the first problem-solving approach that we studied was called Transform and Conquer, and we did it across the episodes Season 1, Episode 3 through Season 1, Episode 7. Altogether, we have dedicated 5 episodes to the study of this problem-solving approach. And usually the very first episode is the episode where I explain slowly and thoroughly, usually without leaving any stone unturned, exactly how this specific problem-solving approach works. So if you never heard about this or that problem-solving approach, you fast forward to this, for example, Season 1, Episode 3, and at the beginning of this episode, boom, I will explain how the Transform and Conquer problem-solving approach works. I will not go over the details of these things. Also, don't forget that this approach, all the episodes that pertain to Transform and Conquer problem-solving approach live in the Transform and Conquer playlist. Exactly. Basically, in 2 seconds or less, if we want to apply the Transform and Conquer problem-solving approach to the process of generating a solution to this or that technical problem, we should follow 2 basic ideas. On the one hand, we want to preserve the technical essence of the given problem because it is this problem that we want to solve. On the other hand, we want to transform the material in that problem into a different setting that honors the technical essence of the original problem, but in a setting that gives us a technical advantage. For example, in 2 space, we may want to reflect the given material in a circle with negative or positive power. In 3 space, we may want to reflect the given material in a sphere with negative or positive power, solve the problem in the reflected settings, and then reverse transform the material back and thus generate a solution. The second problem-solving approach that we studied was called Reinterpret and Conquer. We did it across the following 4 episodes from Season 1, Episode 8 and Season 1, Episode 9. That is what our program for the first season ended. And then we picked up the material from Season 2, Episode 1 and Season 2, Episode 2. That means that I explained the mechanics of how the Reinterpret and Conquer problem-solving approach works. Right here, Season 1, Episode 8. If you missed it, this is the place to start with. 4 episodes, and Reinterpret and Conquer, again, is a playlist. All the episodes that pertain to the Reinterpret and Conquer live in that playlist. And again, in 2 seconds or less, Reinterpret and Conquer problem-solving approach works in such a way that, again, we want to do 2 things. We want to preserve the essence of the technical problem at hand if we want to apply the Reinterpret and Conquer problem-solving approach to the process of generating a solution to this or that problem. And on the other hand, we want to, in some sense, spin or rotate or tilt our problem in such a way so as to reinterpret the local material in a way that is advantageous. For example, when we're given numbers, we may as well interpret these numbers, for example, as roots of a polynomial and then apply the Vieta theorem and formulas to, for example, uncovering the sum or the product of these mysterious numbers. On the other hand, we may interpret numbers as, for example, massive points, and then using the geometry of massive points, we can compute, for example, a sum of these real or maybe even complex numbers. Problem-solving approach number 3, called reverse order. I explained the mechanics of how that problem-solving approach works in Season 2, Episode 3, and we carry the solution of problems using the reverse the reverse order problem solving approach through season 2, episode 10. You can see 8 episodes, no less than 8 episodes we dedicated to that problem solving approach. The playlist is called Reverse Order. Be my guest, find this playlist and go to town on working with the material. This is quite powerful. Basically, again, in 3 seconds or less, sometimes we can assume that the solution of the problem was somehow generated. Initially, we do not care how the solution was generated, but we assume that it was. And then analyzing the state of affairs in reverse time flow or in reverse flow of causality, sometimes we can unwind our steps back from the solved state into the original not solved state. And that reverse flow of causality journey may help us generate a forward flow of causality solution. A beautiful, powerful problem-solving approach. Space-time was the 4th problem-solving approach that we studied across 4 episodes, starting with season 2, episode 11 and ending with season 2, episode 14. Again, if you want to hear the mechanics of how this problem-solving approach works, find and watch season 2, episode 11. And again, in the lightning round, the name of this problem-solving approach sounds a little fancy, but basically the gist of this problem-solving approach is to realize that 4 useful combinations of space and time exist. For example, same space, same time, same space, different time, different space, same time, and different space, different time. And sometimes it is actually quite amazing how students, or even I myself, overlook the idea that the simple zooming through these 4 possible combinations can help us unlock a solution to this or that problem. For example, we can ask ourselves, what will happen if we separate the material at hand in space but not in time, or maybe in time but not in space, and so on, and take the development of the solution from there. The problem-solving approach number 5 is absolutely fundamental equation. It works miracles and wonders in, for example, chemistry, where we balance all sorts of chemical equations. It works obviously in mathematics. It works in some sense the entire theoretical physics, the fundamental, the foundational idea of theoretical physics rides on a notion of equation. And again, I explained the mechanics of this problem-solving approach in season 2, episode 16. We end the dedicated study of this approach with season 2, episode 20. We spent 5 episodes on this problem-solving approach. Again, all the material that pertains to the dedicated study of this problem-solving approach is collected in the equation playlist, just like space-time and reverse order. All these guys, all these problem-solving approaches, all the episodes that pertain to these approaches live in their corresponding playlists on the front page of the channel. You can click on playlists and study things there. But again, if you want to hear how the equation problem-solving approach works, we use season 2, episode 16. Find that episode. And again, in mathematics and in physics, this problem-solving approach, or the whole idea of constructing an equation, sometimes it could be an algebraic equation, a trigonometric, maybe a differential equation. And again, the entire layer called mathematical physics all revolves and boils down to this: first constructing usually a system of differential equations, and then finding a way to solve them. So this covers the first 5 problem-solving approaches, and in the next segment we will look at the remaining 6. As a reminder, across seasons 1 and 2, we have studied 11 altogether, 11 problem-solving approaches or heuristic templates that may help us uncover a solution of this or that technical problem. We covered the first 5 problem-solving approaches in the previous segment, and in this segment we will cover the remaining 6. You can always construct the table that you see in front of you on the board on your own using the links to the free PDF files in the comments section to this episode. These are the links to the so-called season guides that I store in my personal GitHub repository. These files are completely free of charge. Click on the link, open up the PDF file, and construct the similar table on your own. But as a time saver, if you want to, for example, teach mathematics and organize, for example, mathematics and or physics circles, you can use the material that we present in this season guides and follow the ideas and the problems that we present in our program. So, for example, you can bookmark this episode and come back to it at will. And in this table, across 4 columns, I show the number of the problem-solving approach in chronological order, the name of the problem-solving approach itself, the episodes in which we carried out a dedicated study of that approach, and the name of the playlist on the far right in the rightmost column. You recognize the symbol up there. It's a playlist, and again, the name of the playlist, which you can always find in the playlist section on the front page of this channel, matches the name in the clever maneuver, matches the name of the problem-solving approach. As such, the problem-solving approach number 6 that we studied in our sequence was the so-called scope reduction problem-solving approach. I explained the mechanics of the scope reduction problem-solving approach in this here season 2 episode 21, and we spent the total of 4 episodes in a dedicated study of how that problem-solving approach works. Through episodes 22, 23, and 24 was the last episode where we studied that problem-solving approach in a dedicated manner. But again, remember that the moment we finished a dedicated study of this or that technical problem-solving approach, that does not mean that you should forget all about it and throw it out. On the contrary, you should put it into your toolbox and use it the next chance you have when you solve the next technical problem. All the episodes that pertain to the scope reduction problem-solving approach, of which there are 4, are placed in the scope reduction playlist. In the lightning round, in 3 seconds or less, the idea of the scope reduction problem-solving approach is to basically, in plain English, gradually peel away the perceived complexity layers of the given problem until we can recognize in the more and more simplified problem a problem that we solved previously, and thus comes the phrase reduce the current problem to a previously solved one. And then the idea is that in this gradual process of peeling away the levels of complexity from the given difficult to solve problem may actually help us, once we manage to reduce this problem to a previously solved one and obtain the solution of the problem that we can solve, gradually climb back out of the hole step by step, again adding on, in some sense in reverse order, adding on these layers of complexity and attacking each one in turn and overcoming, winning, and so on until we climb out of the hole and solve the original problem. The problem-solving approach number 7 that we studied was a close cousin and in some sense a mirror reflection of the scope reduction, because this problem-solving approach is called scope expansion. And no matter how not intuitive it may sound, sometimes instead of, intuitively speaking, reducing the complexity and reducing the scope of local material, it is possible to solve a given technical problem by doing the opposite, by expanding the scope of the material. And we study this problem-solving approach in a dedicated manner across episodes season 2 episode 25 through season 2 episode 30. Altogether, we spent 6 dedicated episodes to the study of this approach. All these episodes live in the scope expansion playlist. Again, you can always find it on the playlist section of the front page of this channel. I explain, remember that the very first episode that opens a dedicated study of this or that problem-solving approach is the episode where I explain slowly and thoroughly the mechanics of how exactly does this problem-solving approach work. I use or try to use as simple material as possible, usually reducing to the material to the level of middle school. There is no point in studying for example, some new idea and use the notion of kernels or group homomorphisms, because how many people out there who study mathematics initially know what a kernel of a group homomorphism is? So instead of fighting two battles of fighting the tool and fighting the problem, we would rather concentrate on learning how to use the tool and fight this one problem at a time and forget about the local material. The local material should be as simple as possible, but not simpler. Now, the scope expansion, to give you a quick example in the lightning round, for example, we can use the idea of scope expansion when we evaluate the sums of integers, consecutive integers raised to integral powers, instead of considering the sum, for example, of integers raised to the power 2. Magically, we bump up that power from 2 to 3 and seemingly complicate matters, but it turns out that the miraculous way in which mathematics works, this specific scope expansion actually helps us solve the problem, and that is how we win. The problem-solving approach number 8 is called Eliminate and Conquer. It was made popular in the Western literature by Arthur Conan Doyle through his immortal character of Sherlock Holmes. When everything that is impossible has been eliminated, then whatever remains, no matter how improbable, is the truth. We study this problem-solving approach across Season 2, Episode 31 and Season 2, Episode 36. Altogether, we spent 6 episodes studying this problem-solving approach. All these episodes live in the playlist called Eliminate and Conquer, and I explain the mechanics of how this problem-solving approach works right here. Season 2, Episode 31, the very first episode in the sequence of the dedicated study of this problem-solving approach. And remember, when it comes to this guy, remember that there is a fundamental flaw that is built right into the DNA of this problem-solving approach, because this problem-solving approach has absolutely zero predictive power when it comes to guaranteeing whether the culprit was lassoed into and rounded up in the initial scoop when we try to incorporate all the suspects put all the suspects into one bag and then start eliminating them one by one. Because what will happen if we did not round up the usual suspect in that process? Well, that means by the time we eliminate all the suspects that we did manage to grab, we will eliminate all of them, and voila, we will have no way to solve the problem. So here we have to pay attention. There is an inherent problem with this problem-solving approach, even though when it works, it works. Sometimes, though, in order for us to guarantee that we did lasso in the suspect into our pool of suspects, the amount of computational work that we have to carry out may be simply unfeasible or way too much that a human can handle. The problem-solving approach number 9 was divide and conquer, another very popular, very powerful approach for solving problems that travels well throughout the entire physics, mathematics, and elsewhere, even in real life. We study the mechanics of how this problem-solving approach works in Season 2, Episode 37, and then for 7, no less than for 7 episodes, we look at the examples of how the divide and conquer problem-solving approach works, terminating that dedicated study with Season 2, Episode 43 over here, 37 through 43. All these episodes live in the playlist called Divide and Conquer, 7 episodes, explanation of how it works. If you missed it, zoom into Season 2, Episode 37, work your way through the material that we present on this channel in this episode, and voila, begin mastering the application of the divide and conquer problem solving approach to the process of generating a solution to a technical problem. And now comes the time for the remark that I made in the previous segment, that in general you can study and work through the material that we present across these 2 seasons, Season 1 and Season 2, when we study this problem solving approach in a dedicated manner any which way you like. You can hash all these problem-solving approaches chronologically any which way you like. The chronological order that I presented here is just my personal choice. You can pick a different one, but remember that these two guys, the invariant and the mathematical equivalence, they are the invariant problem-solving approach. It is not as much it is that it is technically demanding, but it is new to many students, and this problem-solving approach, along with this one, of course, wears the better the more experience you have in mathematics, because in this problem-solving approach, okay, let's discuss this. Okay, so the approach number 10 was called invariant. I explained the mechanics of how this approach works in season 2, episode 44. Then we can dedicate no less than 7 episodes to how this approach works, terminating the study with season 2, episode 49. All these episodes live in the invariant playlist. And the deal with the invariant problem-solving approach is that it sometimes helps us generate an answer to a problem that does not seem to be solvable initially with the amount of information that we're given. And secondly, it has the following flavor. For example, in real analysis, we have an impressive battery of so-called convergent tests. We can take a given infinite series, look at its common term, apply one of the well-known convergence tests and say yay or nay, for example. If the convergence test says that yes, this infinite series does converge, usually this is the only answer that this convergence test can produce. It cannot tell us to which, for example, real or complex number does the series converge. So in some sense, these answers, they give us information, but this information is not fully descriptive, it's not fully constructive. It only assures us that yes, the given series converges, but we do not know the name of the real or the complex number to which the series converges. The invariant problem-solving approach carries the same flavor. Quite often, it gives the non-constructive answers or solutions to the problem, to various problems. And that is the only thing that the invariant problem-solving approach can produce. And a lot of times, the essence of this problem-solving approach is to look at the initial state of the problem, analyze the material in the problem, then realize that a certain combination, maybe a difference or maybe a residue of a difference, residue of a sum, can remain one and the same throughout every step of the process. And then in the initial state, it also must be the same. And then if we compare, for example, this value of the invariant in the initial state, value of the invariant in the final state, if these values match, then due to the fact that this magnitude or quantity is conserved, remains one and the same, we can make a conclusion, yay or nay. And sometimes when the conclusion is positive, we do not really how the exact sequence, the algorithmic beat and flow of how this sequence of steps can lead us to the final state, but we do know that, for example, that particular state can be achieved. So that's why it takes a little bit of mathematical experience and mathematical maturity to juggle the local material and fold it into a useful invariant, because remember, in season 2, episode 44, I explain how the invariant problem-solving approach works, and one of the things I say is that not all invariants are created equal. And it takes, again, time, experience, knack in selecting the invariant that will help. And in some sense, this is more of an art than a science, even though, of course, science has a lot to do with the application of this approach to the process of solving problems. Now, the last, so to speak, problem-solving approach, number 11, called mathematical equivalence, we study across 4 episodes, starting with season 2, episode 52, where I set things up. Here you have to be careful because I switch gears a lot. This problem-solving approach is quite demanding. It's technically challenging. You definitely need mathematical experience and maturity. The application, a successful application of this problem-solving approach to the process of unwinding a solution of this or that technical problem, does require certain higher power of abstract cognition, the control and command of the technical tool, the tactical prowess. For example, shuffling differential equations. Quite often, if we can reduce two verbally different problems to one and the same differential equation, then we know that in the theory of differential equations, the so-called existence and uniqueness theorems are the bread and butter of that layer of mathematics. As such, if we reduce two verbally different or descriptively different problems to one and the same differential equation or a system of, then we know that, for example, that equation has a unique solution. Hence, we say that the underlying structure of the solutions of these two problems is one and the same. And then, even though verbally and descriptively the problems are different, mathematically they are what? They are equivalent. Exactly. We study this approach across 4 episodes, like I said, but the essence of this approach, again, precisely because it's what perhaps the most challenging and the most technically demanding of all, you really should study this guy, this problem-solving approach last. Reserve it to the last study, because the essence of this approach, again, will dawn on you only if you gradually work your way through these 4 episodes in that sequence. I recommend that you guys do it in this sequence: season 2, episode 52, 53, 54, and then 55, because here, in order to demonstrate how this approach works, in season 2, episode 52, I set up a case where I take 2 problems that even in their solution come tantalizingly close to each other, but they fail to be equivalent. In other words, it is not possible to mechanically, with zero tactical and intellectual effort, to take the solution of one problem and plop it onto the solution of the other, or conversely. But when and if the mathematical equivalence does work, this is precisely what we can do. We can take one problem, reduce it to, let's say, one and the same differential equation, and say, look at this. We already know how to solve this differential equation because we already solved it before. And that means that this problem, even though verbally it's different from the original one, has exactly the same structure of the solution. We just have to carefully shuffle the flow of time and the initial conditions, and voila, mechanically, we take the solution of this differential equation in general and boom, sculpt it into the solution of the problem that we're trying to solve. All the episodes, again, in season 2, episode 52, we show how things fail. And then in season 2, episode 53, we solve the so-called Lanchester's square law problem, or the problem of 2 armies fighting in the open. In season 2, episode 54, we solve the problem of a massive bead sliding without friction along the absolutely rigid massive rod that rotates in the horizontal plane with a constant angular velocity. Fighting armies, rotating rigid rod. What do they have in common? Seemingly nothing. In reality, they are mathematically equivalent. And we develop the solutions of the problems, season 2, episode 53, and season 2, episode 54, in a completely isolated way from each other, without assuming or pretending that we do not know the solution of the other problem. But here in season 2, episode 55, here bucking the trend and reversing the idea that first I explain how the method works, then we solve a bunch of problems. Here we solve several problems, and then in season 2, episode 55, we do witness how these things work. So reserve this problem-solving approach. I suggest that, you're free to do whatever you like, but I suggest that you reserve the study of this problem-solving approach to the last. Now, this list is not complete. This list of problem-solving approaches, by all means, is not complete. There are a couple other ones, but in my humble and professional opinion, the 11 problem-solving approaches that we studied across season 1 and season 2 on this channel are the heavy hitters. They're the popular ones. They provide already an impressive toolbox with which we can go at it at technical problems. There are a couple other problem-solving approaches that are out there, and maybe I will explain it as we go along. And here, the thing of note is the following. Yes, we sort of trained our microscope, if you will, on every particular situation. for which each individual problem-solving approach works, and that is why I hinted with the demonstration image that you saw at the beginning of each segment that each and every problem-solving approach that we studied so far can be represented as a musical note, and the experience of listening to a tune which is played note by note versus the experience of listening to a piece of music where the individual notes are combined into a harmonious chord is quite different one. And here is the thing: we now learn the notes, but in reality pretty much all the even more or less serious problems in mathematics, physics, and elsewhere are never or virtually never solved with a single problem-solving approach, but they are solved with the combination of these approaches. And that is why the analogy I think over here is appropriate, that each individual problem-solving approach is a musical note, but in reality, when we solve a realistic problem, we usually combine these approaches in certain order. We hash them together, we mesh them together, we smash them together, and sometimes in the end it comes out as a total jumble and it seems like we have no idea what we're doing. But if we're solving a problem correctly, then somewhere in the midst of your solution there sits some number of problem-solving approaches that is glommed together in certain order, in certain sequence. And now from this point on, we are solving the technical problems in mathematics, physics, and computer science in a never-ending sequence, and we return to our regularly scheduled programming where we do just that. We solve problems, and the first problem of season 3 will be the mathematical problem S3E1.